So here's some more examples on drawing cells or doing the problems drawing voltaic cells, which is question number 1 on your next assignment. So for each of the following cells, use the given cell notation to determine the strongest oxidizing and reducing agent. So again, with cell notation, cathode is always on the right, anode on the left. Okay. So we want to label strongest oxidizing agent, reducing agent. So because we know this is a cathode, our strongest oxidizing agent has to be on this side. So in this case, it's going to be over here. Okay, strongest reducing agent would be over here. Okay, so we can do that. If we didn't know that, again, you just look through your booklet, okay, and find your strongest oxidizing reducing agents. Okay, and so like silver is right here. Okay, and then way further down is zinc is down near the bottom as it down here as an oxidizing agent, or it's a strong reducing agent. And so you can always use that booklet to kind of see strongest oxidizing, strongest reducing agent. Okay, so we have those. Okay, write the chemical equations to represent the cathode and anode, and then net cell reaction. Okay, draw a diagram of each cell, labeling electrodes, electrolytes, direction of electron flow, and direction of ion movement. Okay, so we start label, or we always want to write our half reaction first for our strongest oxidizing agent. So silver plus 1 electron produces silver solid. And then our other one, we have zinc solid is going to produce zinc 2 plus 2 electrons. Okay, overall reaction, we have to times everything in the first one by 2 to balance out the electrons. So we have 2 silvers plus zinc solid. It's going to produce zinc 2 plus and 2 silver solids. Okay, so that's our overall reaction. Okay, so this is at our cathode. This is at our anode. And that's kind of the overall reaction that's taking place. The ions are moving from our anode to our cathode because it's losing them and giving them to our cathode. Okay, so again, now draw our 2 containers connected by a salt bridge. So this is kind of the first step for all of these. They're all going to look the same. Okay, so this is kind of what they all look like. They'll all be connected by a wire or external circuit. And it doesn't matter, pick which side. So like, let's say this is our cathode, meaning that this is what we have at our cathode. We have, that means this is silver solid, and then in here we have silver plus, which is aqueous. Okay, we put our little porous ends on our salt bridge here. Okay, that means this is our anode, which makes this zinc solid, and then we'd have zinc 2 plus in here. Okay. Again, from in our salt bridge, we label our direction of ion flow. So the anions will go towards the anode, cations towards the cathode. Sometimes they'll say what's in the salt bridge, and then you just write, like instead of anions, you'd say like NO3 minus goes towards the anode, and sodium plus goes towards the cathode, whatever which way it works. And then the direction of electron flow, okay, again, is always going from the anode to the cathode. Okay, and so looking back at kind of what it wants, so we got the chemical equations at the cathode, anode, and the net cell reaction. So this would be our net. Okay, draw a diagram of each cell, label electrodes. So our electrodes are anode and our cathode. Electrolytes, that's what we have here. Okay, direction of electron flow, okay, that's in our external circuit, and then our direction of ion flow, that's in our salt bridge. Okay. Okay, next example here. Okay, we're on page 7 of our notes. Okay, again, this is our cathode. We know that because of cell notation. This is our anode, meaning that this has to be our strongest reducing agent. Okay, and this has to be our strongest oxidizing agent. Okay, we have in this one we have an inert electrode. Okay, so it won't be involved in our reaction. Okay, so it won't be involved in our reaction. Okay, but it is there, and so like when we're drying it, that's what's going to be one of our solids. Okay, and that's what actually that'll be our cathode in this case. Okay, so we want to write down our two half reactions. Okay, so in this case, at the cathode, our half reactions, the nitrate plus hydrogen. And so that we can find out of our data booklet. Okay, but basically we have 2 NO3 minus plus 4 H pluses plus 2 electrons. It's going to produce N2O4 gas and 2 waters. Okay, so that's just straight out of our data booklet. Okay, and then at the anode, okay, we want the oxidation half reaction, so aluminum solid is going to turn into aluminum 3 plus and 3 electrons. Okay, now we need to balance out our electrons for our net reaction, so we're going to times everything in here by 3, everything in here by 2 to get our net reaction. And I'll write that down and then come back. All right, so that's our net reaction here. Okay, now we draw out, again, start with our 2 beakers, draw our salt bridge, a little porous boundary on the ends of those, our solution, and our 2 metal electrodes. This solution won't go through the electrodes, but okay, doesn't matter again. This time let's put the cathode over here and the anode over here. Okay, so we said at the anode we have aluminum solid. Okay, again, anode's negative, cathode's positive. Good thing to get in the habit of writing down. Okay, over here this is platinum, okay, which isn't actually part of it. Basically, it just allows the electrons somewhere to flow through its electrode, electric or current carrier, and so we can get the current in here where it's needed to then form like the NO3 minus, the nitrates, and H plus. Once the electrons come through, they're actually going to give off of this N2O4 gas. Okay, so at the cathode, it's actually we're going to get some bubbles in here because this gas is going to be given off. Okay, over here, we got Al3 plus in our solution, and this is going to start to deteriorate, and so actually like different bits will come off of this to form this as the electrons go from the anode to the cathode. So our electron direction in this case is going this way, and then our anions go into our anode, cations to our cathode. Okay, so that would be full marks there. And you wouldn't have to show this. I just want to show you as an example. Like you will get questions. They'll say like, where are the bubbles going to form, or why are the bubbles going to form? Well, this is producing a gas at the cathode, so this would be our bubbles in that case. Okay, and it might ask like, what's breaking apart? Okay, the anion will break apart. This again is just a solid conductor, just to allow the electrons to pass through. Once the electrons pass through and meet up with our oxidizing agent, okay, it'll start producing our product.